Here you
I'll
go.
start in like a minute.
Sounds good.
Yeah. Yes. Oh. Kate, can you hear us right now? Or you can hear me all right? Yes. Okay, thanks. All right, let's get started. It's 2:10 already, so we'll get started with class now. Welcome to lecture week 3. So here's the attendance QR link as usual. And if you guys don't have Wi-Fi right now, don't worry, you can do it like after class or just like in the next few days is fine. So some announcements before class. Everyone should have just turned in homework 1. Hope everything went all right with like submitting the Jupyter Notebook to B courses. The second homework was already released and it'll be due on Tuesday. So here's also the link for the attendance form. And we also have office hours scheduled in Campbell 121. We basically have a slot for every single day of the week. So you guys should definitely come to like get any help. And my office hours will be right after lecture today. The room's just right next door. So like after lecture, we can just go over there. Yes.
There you go. Okay. Yo, you gotta show me how to do that.
Okay. Okay, so short recap of what Isla taught us on Tuesday. We first went over Boolean statements. So these are basically true and false statements. So something like false and 1 is equal to 2. And so this would return false since 1 or more of the statements are false in this and statement. Isla also talked about if statements. So basically you would do if and then a Boolean expression. And if the Boolean expression is true, it'll then execute whatever you have underneath. We also went over for and while loops, and these are really useful for if you want to iterate over something or iterate over a range or a list of objects. Yeah, so going more in depth on while statements. So you basically use this when you want something to happen as long as whatever condition is true. So how you would format it is you do like while and then a Boolean condition, and then you have your code underneath. And then each time it'll keep doing it until the condition is false. And so it's really important to make sure that you're changing the condition every time in your loop so that eventually it does become false. Otherwise, the loop will just iterate forever and your code will kind of start to break. Yeah, it's also really important to look at like the colon and the tabbing. So basically anything that's tabbed is in the while loop and everything that's unindented is not in the loop and will execute normally. And then for a for loop, it's a similar idea of iterating over something multiple times. This is used more for when you want to iterate over a list of things. So if you have like for object in a list of objects, you can do something for each of them. And so there's not necessarily a Boolean condition, but still really useful. And both of these can be used interchangeably sometimes. Okay, and so to start off lecture today, we'll start with a short discussion activity. So you guys can work in small groups and like, I'll give you like 5 minutes to work on it. So basically if everyone could just try to write a function, factorial, that basically computes the factorial of a number x. So for example, factorial of 3 would just return 3 times 2 times 1. Yeah, and so if you could try to do this using a for loop or a while loop, both should work. If you would use a for loop, a small hint that I'd give is that you can do like for blank in range blank, and this allows you to loop over a range of numbers. Yeah, so I'll give you guys like 5 minutes to work on that, and then we'll like go over it together.
Are you recording?
Yes.
Emily, you want us to walk around and help her?
Yeah, I can do that for like a minute. But yeah, that'd be good. Yeah, I feel like
Are we all doing over there? So, I guess, thought how many like ideas that we thought maybe could work or like yeah, so there's more than one way to do this. So you can do it with wild circles. And either way, we need to figure out a way to like one, right? Because you like factorial definition is like if it's n factorial, you multiply by n, or multiply n by n minus one, all the way down to one. So a good way to iterate through all those numbers would be to say for like I in range whenever you're n, right? Or maybe plus one or something. And but then you're just multiplying each I with each other. So you might want to figure out a way to store what I was on the previous iteration as well as this one, and then to multiply the new iteration.
Oh, okay, I know like everyone's probably still working on it, but just for the sake of time, we'll just go over it now. Yeah, let me pull up the Jupyter notebook. Okay, so does anybody have a idea of like how to start or like how they started, and we can go from there. Yes.
You make a variable to store the product that you can eventually return.
Okay.
And then you can set up like the loop of your choice to link through like
Okay, yeah. So if you guys didn't hear, basically what she was saying was that you can first make a variable that you would return at the end. So you could do product equals 1, because we know we want to multiply something by this product each time and like slowly increase it. And then use a for loop to kind of loop over the other numbers and multiply them in as well. So we can try that. So I'll have product equals 1. And then in my for loop, I'll just do for I in range. And so range, the smallest number is inclusive and the larger number is exclusive. So in this case, we'd want to do, we know our largest number would be like X, and our smallest number we want to multiply would be 1. So we could just do for range and 1 to X plus 1. Yeah, and as she was saying before, we basically want to multiply our product by the new number in the range 1 to X each time. And so basically how we could do this is by doing product equals product times I. And then we can just return product. And so if this should work, we should be able to do factorial of 3 and get 6. So let's see. Yeah, does anyone have any questions? Yeah.
So what about like the, I guess the I?
Oh yeah, so if so since we're doing a for loop, the I is getting incremented each time automatically for us, so we wouldn't need to do that. But if you're going to use a while loop, we would need to increment our counter. And so we could also use a for loop. So let's do while factorial. And so we could also start with product equals 1. And then we could do something like, so if we want to do like you were saying, increment I by 1 each time, we could start with like I equals 1. And so then we have like while I is less than or equal to X, right? And then we would just say product equals product times I. And then here we would just increment I like you were saying. So I plus equals 1. And then still return product. Okay, and let's just see while factorial of 3. And that also equals 6. So we are good. Yeah, questions? Yeah, that's a really good point. We didn't really account for edge cases in here, but exactly like you were saying, if we wanted to kind of like use this in the real world and not just this exercise, we should definitely add that as well. So we could say like if x equals 0, return 1. And so since we would return 1, we wouldn't execute any of the other code. So now if we have while factorial of 0, it would just give us 1. Yeah, does anyone have any other questions about this? Okay, yeah, so the question was, since we're using an if, do we also need an else? So in this case, we don't really need an else, just because if this if statement doesn't happen, it'll automatically just continue where we left off in the code and do the rest of it. But if we wanted to, we could add an else and it would be the same, as long as we didn't. Yes. All right, so that was just like a quick warm up to remember what we learned from last lecture. Yeah, so let's get into what we're doing today. So today we'll be learning about dictionaries, and this is like the last built-in data type of Python. So it's really exciting. You know, we're almost there. Yeah, so it's similar to kind of a list or tuple that we've already seen before. And basically, it's just another structure to store data. And what's really good about a dictionary is that a lot of times we want our data to be stored with a label, so it's easier to organize and find it later. So basically how dictionaries are stored is that there are key and value pairs. So the key is basically the index of a dictionary, and the value is the data associated with a certain key. So if you actually think about, so if you actually think about a dictionary, like the key would be like a word you're trying to look up, like astronomy, and then the definition would just be like the study of, you know, outer space, etc. And that'd be the value associated with it. And so similarly here, if we have our dictionary called Roman numerals, basically the keys would be like the strings of X, V, and I. And if we looked up in our dictionary what the value associated with X is, we would get 10. And so it's a lot of times it's easier to organize things in a list because you can label them as well. Okay, so here's how we actually create and fill a dictionary. There's a couple of ways to make an empty dictionary. You can just use the curly braces or type in Python recognizes the word dict parentheses because it's just making an empty dictionary. And then if you wanted to fill a dictionary, you would just do the name of your dictionary and then brackets and like the key equals the value. And so we can also use any sort of data type as a key. It doesn't necessarily have to be a string. So you could do something like 10 as your key or another list or something if you really wanted to. But yeah, so in the example here for days of the week, we first create an empty dictionary, and then we can add a value of Monday, and that would just be associated with the key of 1. So if a lot of times we'll want to take a list we already have and make it a dictionary instead of just starting from an empty dictionary and adding every entry in one by one, since that would be really slow. So you can also just have your curly braces and then do your key colon value and then separate all of those by commas. Or also you can again use the built-in word dict and then just put a list with the key value pairs in like parentheses. Yeah, but anyway, so you don't have to exactly like memorize the syntax. You can always just look it up on Google or look at these slides again. But yeah. Okay, and so then after you've made your dictionary, you'll probably want to actually look up your values at some point. So you can either just do the name of your dictionary, bracket the key name, or you can use d.get key. So here we can see the Roman numerals of I, and we get the value back of 1, since that was the value associated with the key. And similarly, we can use .get instead, and get the value of 5 for the key of D. And so these are totally equivalent. It's just whichever way you prefer and like whichever way you remember better. And then, so let's say if you want to delete a key in your dictionary because you say you don't need it anymore, you'd basically just use the keyword del, short for delete, and you would just do the dictionary name and the key. And so this actually won't output anything, but it'll just delete it in place. And so if you ever want to look at all the values in your dictionary or all of the keys, you can just use the built-in function as well. You can just do the name of your dictionary .values and similarly do dictionary.keys. And you can see here, it'll just return a list of either all of the values or the keys in your dictionary. Yeah, does anyone have any questions about that so far? Mhm.
Cover all the things.
Yes. Do you mean like if you add a something to it in a line, will it remember everything else you've already added? Kind of? Yeah. So as long as you use the same name of your dictionary, it'll remember everything you've already added to it. Since like the name of the dictionary is tied to like everything in it. So here, if we added another line of like days of the week, bracket 2 equals string Tuesday. In the end, days of the week will be a dictionary with 2 entries of like Monday and Tuesday. So if you had a list, so that would just be like the square brackets. So basically, if you want to index anything in the list, you would have to do like list, like bracket 2, and that'd be like the position of it. But for a dictionary, like we saw in Roman numerals, you can make your keys not just integer numbers. So it kind of makes more sense for some of your data sometimes. If we want to make this a list, we would have had done like Roman numerals and done like 10, 5, and 1. And then if we wanted to find the value associated with 10, we would have done like list of 0. But here it's kind of more intuitive because you can just do like your dictionary of X and then get that value 10. Yeah, you can sort it. Although in general, when you just put in entries in a dictionary, it's unsorted. So usually what you would do is you would get all the keys of it, and that would be a list, and then you can sort that list kind of. But yeah, you can sort them too. Okay, so all the keys are unique. So let's say we had like X equals 10 as our first entry, and then we made another entry of like X 15, it would just override the original entry. And so like in the end, your X entry would just have value 15. Oh. My speaker. I think it's fine. It said your speakers might not be working.
Is tape on the ball?
Okay, let me ask. Oh.
Oh yeah, just turn off.
Okay. Cool. Okay, you can still hear me, right? Okay, we're gonna assume yes. Oh. Yes. Okay. Yeah. Question. Yeah. In Python, you don't have to have all your keys and values matching of the same type. So yes, if we want to do like X is 10, and then for a different entry, we wanted V to be like the string 5, like that would be totally fine. Okay.
If it pops up again.
Yeah, I think it's fine, right? Okay.
Oh, you know what it might be?
Yeah.
Sorry for the technical difficulties. Go to sound. Okay. That should be fine. I think everything will be working. Sorry about that.
Okay, yeah, and so if this is a more astro-related example, so say we had a supernova, we could put in the entries of the dictionary all the different fields we're keeping track of, like apparent magnitude, 2.9. And yeah, as you can see here, like we were asking before, can your keys be different types? And yeah, they can totally be different types. Okay, yeah, and so now I'll switch over to the demo. So I sent out an announcement earlier today. I don't know if most of you saw it, but we'll just be working in the Jupyter notebook from before. Yeah, so basically, first, if I want to do a dictionary, keeping track of all of the planets in our solar system and like the value as how long a day is for them in hours. So if I wanted to create an empty dictionary, I would just do the empty curly braces as we saw before. And then if I wanted to add an entry for how many hours in a day on Earth, can someone tell me how we would do that? Yeah.
So,
Okay. Mhm. Yeah, so we could do 24, like she was saying. And so this would add, so yeah, so now if you look at our dictionary, we have one value in there, just Earth and 24. And so if we wanted to do another one, we could similarly do like Mercury equals 1416. And so now if we output planet days again, you'll see that we have two entries in there. And so obviously it was really slow watching me type in line by line. And so if we wanted to, since we already have the planet day and hours list that I kind of looked up before, we could instead just do dict of planet day and hours. And this will also just create the dictionary with all of the entries in it. Okay, so now let's say that we wanted to write some code and actually do some calculations with our dictionary. If we wanted to compare the ratio of an Earth day to other planet days, so basically like see how long are these days actually compared to Earth, we could do for planet and planet days dot keys. And so basically we know that all of our keys are the strings of the planet names. So we'll be looping over all of the planet names in our list. And so for each of those, we can then, so we first want to get the value associated with that key. So we could do planet days of planet. And then since we want to basically divide it by an Earth day, we can reassign this to planet days of planet and then divide that by 24. And so, oh yes, forgot about that. Okay. Yeah, so now if we run this again, wait, probably made a typo. Planet days, ooh, just kidding. Okay, so if we want to do, yeah, so if we want to do planet days, okay, wait, let me look this through. Planet days of planet equals, oh, I think I ran it twice, which is why it was being weird. Okay, yeah, so if we see now we how we changed all of the values in our dictionary. So now they're now in terms of how long an Earth day is. So we can see like Earth obviously is like 1-to-1 ratio. And then we can see that Venus has a way longer length of their day. That's like 243 times Earth's day. And then comparatively, like Saturn is basically half an Earth day. Yeah, and so now let's say we wanted to delete a key just because Pluto is not actually a planet. Does anyone remember how we would do that part? Yeah. Okay. Yeah. So if we just do del and do planet days of Pluto. Yeah. And so then if we look at planet days again, oh, okay. It's because it ran it twice. So let me go back a second. But yeah. So if you look at planet days now, there is no Pluto. Yeah, so does anyone have any questions on dictionaries? Okay. Oh, yes. Yeah. Yes, so we could do this. We could have also done planet days equals. So either of those would have been the same empty dictionary. Yeah, and I'll like post the demo again with everything completed. So if it's okay if you don't like copy everything down now. But yeah, so that was pretty much it for dictionaries. And so for the rest of lecture, we'll be doing some more like advanced Python things. And these might be really confusing. So it's okay if you don't totally understand everything. You probably won't need this on a day-to-day basis, but it's just good to kind of get used to seeing some of these things and like starting to understand some of like more computer science topics. Yeah, so first we have like another way to make functions, and you can do this by doing lambda functions. So this would be the exact same function as if we did like, def quadratic and then did like return x to the power of 2. But since it's just one line, a lot of times people will like simplify their code by just using this lambda keyword. And this is a word that Python already recognizes. So you could just do quadratic equals lambda, and it'll basically know that whatever follows you want to be a function. And so you would just use your variable x, just what would normally be in your parentheses in your def statement. And then after the colon would just be your return statement. And so this is just, in case like you see this in code somewhere, you kind of know where it's coming from, but you definitely don't need to really like use this on a daily basis or anything. Yeah, and so for the rest of the day, we'll be talking about recursion. And so yeah, CS61A goes a lot into this. So if you guys are curious about learning more, I definitely recommend taking that class. But basically, recursion is really useful because instead of returning like you normally would, like return the number 10 or like return true, you can return a function that calls itself. So basically, you could just call the function itself and it would like iterate multiple times. So yeah, so something like this mathematical expression below, you probably would never need to really code this for anything practical, but just in case you wanted to, the easiest way to do this would be recursion, just because you can see the nested structure of something within something. It's like you're like doing calculations on yourself, kind of. Yeah. So if we look more into it, recursion, a lot of people refer to it as taking a recursive leap of faith. And basically you have to trust that your recursive call will meet the base case eventually and return what you want. So if we look here, we have def factorial of n. And so we wrote this earlier today using while and for loops. And you can see using recursion, the code gets a lot shorter. And it also seems to, and when you first look at it, you're kind of like, how does that actually return factorial? It doesn't really like make any sense. And so that's why it's like taking a recursive leap of faith, because you kind of have to trust that your recursive call will eventually get to your base case of n equals 1, and that'll return 1. Yeah, so more on that. So the recursive case is basically the return call at the end of your function, and you basically return the same function that you're in. And it's really important that you modify the argument slightly in your recursive case, otherwise you'll get an infinite loop, similar to how in a while loop you need to change your conditions. And the base case is the smallest case at the end of a long chain. And this will basically signal to stop the recursive calls and finally start returning stuff. And so if you see like in this picture here, all of the recursive calls would basically be like the reflections that you see, and your base case would be the one reflection at the end that's kind of like doing something different and signaling to the other calls. Yeah, so if we look more at factorial example now, so we would start, let's say if we had factorial of 5, we know that this should be 5 times 4 times 3 times 2 times 1. And so if we walk through the code, so first we would have factorial of 5. So then we would check, does 5 equal to 1? And that's false. So we would do our else statement. And so then we would return 5 times factorial of 5 minus 1, which is just 4. So you can see here, we start with factorial of 5, and then our next call would be 5 times factorial of 4. And then, so now we would start back at the top of our function, and we would have factorial of 4. We would check, does 4 equal to 1? It doesn't, so then we would return 4 times factorial of 3. And basically, like you can see, like the factorial of 4 is basically replaced with 4 times factorial of 3. And so you would kind of continue this recursive chain until we get to factorial of 1. So if we have factorial of 1, we go then to our if statement, does if 1 equals to 1. And since this is now true, we would then return 1. And so then factorial of 1 has finally returned 1, and it'll kind of go back up the stack and return like, 1 times 2 was 2, and then 2 times 3 was 6, and kind of like go back up the stack. And so we'd finally return our final answer of 120. Yeah, so here's also just like an image kind of describing that again. You kind of have your calls, so you end up with a lot of recursive calls, and then eventually these all get kind of compressed back down until you have a final return value. Yeah, and so obviously this seems really like a really complicated way to write code, and you're kind of like, why would I do this? And a lot of times, like a lot of ideas are better expressed as small steps. So we use for loops and while loops to write factorial earlier today, and that was like totally fine for our use case, but a lot of times you will have to use recursion to write stuff. So a lot of times you'll use like tree recursion to express multiple possible paths, or and in general it can also make code much cleaner and efficient, especially when you get to more advanced topics and like more advanced coding things that you're trying to code. But yeah, but for our purposes, we probably won't need to use recursion to write anything really. Okay. Yeah, and so now we'll look at what some demos. Yeah, does anyone have a question? Yes.
I guess for the we did the last. It's like you put in n equals 5. Why does it?
So if I do factorial of 5, so
I guess
so-
like what's the intention of like writing that code? How does it?
yeah, so a lot of times when you're writing recursion, you're not actually thinking about this giant stack necessarily. Like when you approach a recursion problem, you think, okay, so like you have the structure of each time you should multiply by something, and you should multiply by like a smaller number each time. And so you'd write your recursive case of like, you want to basically multiply 5 times all of the smaller values. And that's basically what the recursive call is saying, where you trust that factorial of like 4 will also return, multiplying all of like 4 and all of the smaller values, kind of. And then you know that the smallest case you want to stop at would be if n equals 1. yeah, in that case, you would just return 1. Does that answer your question a bit, or like it's pretty confusing? Yeah, that'd be great.
I just like I think like a good analogy to it, or at least like what I like to think of like a visual representation is like if you ever crack a whip, right? It's in like a chain of instructions, basically. Like the whip goes like it like creates like this kind of trail where it like creates like heat that moves all the way down to the end of the whip. But what happens at the end of the whip? It cracks, right? And then the whip snaps back, basically back to you, like Indiana Jones. So that cracking of the whip at the very end is like your base case, and then it's telling the rest of the whip to come back. And once you have all that information, it comes back. Like at least that's the way I like to like visually think about it. At least for this.
Yeah, like in general for recursion, you trust that you set up the problem correctly and that you set up the end of the correctly, and then you just like assume that the middle will go okay. So yeah, it is hard to write just because it is like building up a lot of intuition in the beginning of how like the two ends can meet. Um, yeah. Okay, yeah. So then for demos, so we can look at say like Fibonacci numbers. We know that for Fibonacci numbers, the sequence goes like 0, 1, 1, where you basically add the two previous Fibonacci numbers to each other to get the next Fibonacci number. So like 2 plus 3 equals 5. So if we wanted to write this with a while loop, we could start with like, the first fib number is 0, and the second fib number is 1, and then have a counter, and then just do like, while the counter is less than n, you would just, and then you could kind of go and add up your Fibonacci numbers like that and return the final one. But yeah, so let's try to do this recursively just because it will be a bit cleaner and it's a pretty good example to look at. Yeah, so let's start with, so first for our recursive function, we need to start with some base cases. So does anyone have any ideas what we could do for our base case of when n equals to 0? Yeah, they said just now it's like 1, because if we think about it, if we called like fib on 1, we would just want to return or fib on 0, we just would want to return the first number. Yeah. Yeah, so similarly, does anyone have ideas for what to do when n is equal to 1? Yeah. Okay, and so then for the recursive call, this step is a bit more complicated, but in general, we know that the idea that we want to kind of capture is that you add the two previous numbers, right? And like you want to return that as your current number. So does anyone have any idea on how we could kind of capture that idea in a return statement? Yeah. Yeah, okay, let's try that. Yeah, because if these both statements aren't met, then it basically will just execute this return and that'll just be else. But yeah, we could also put it in an else. It all is kind of up to you on how you want to organize your code. Yeah, and I think just to be consistent with this one, we define the first fib number as 0. So I'll just change this to 0, just to like be consistent. Yeah, and so you can see like our two kind of ways to write this function both return the same thing. Does anyone have questions on how we wrote this? Yeah, so we could also do like a larger number. Let's try like 100, which is taking longer. That might have been too large. Okay, maybe I'll try just like 10. Or okay, yeah, maybe we'll try like 10 instead. Yeah. Yeah, so if we do this, we'll get the same results as well. Okay, and then for, yes. Oh, I changed this to be consistent, the base case here to be consistent with the base case up top. Yeah. Okay, cool. Okay, so now we saw the really weird example before of all the nested square roots. So yeah, let's try to write this out ourselves and using recursion. Okay, so if we wanted to do square root of 6 plus the next square root of 6 plus, we can kind of see that there is a recursive structure where you can see like each, you can think of the square root of 6 plus something as like one function call. So each time you're just adding on a square root of 6 plus another, like the function itself in a way. Yeah, and so first we can just import math since that's how we'll be doing square root. But yeah, does anyone have any ideas on what we should do for our base cases here? Yes. Square root of 6 x times. The picture of 6 plus dot 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 x times. But yes. Yeah, so for here, we would just do 0. Yeah, but if x equals 1, we'd want to compute it like once, kind of. So for here, we could just do square root of 6. Yeah, so if it's just 1, we would just want to do the square root of 6 kind of as our base case. Yeah, and so does anyone have any ideas for what to do for the recursive call? Yeah. Square root of 6 plus yeah, what do you mean by the function inside? Yeah, so basically we'll have, oh yeah, okay, so square root of 6 plus, okay. Yeah, and then how do you think we should modify x, our argument? Since we definitely know we have to modify it somehow. Yeah, okay, let's try that. Oh, square root is not defined. Yes. Oh. Okay, yeah, and so you can see we have, that is our square root of 6. And so if we try doing this on like 10, we would get more numbers. Yeah, and then we can try to run like a different cell and see if we get like the same answer. So if we have square root of 6, we should get 2.4498. And then if we want to start doing like the recursive thing, we see that if we want to do like square root of 6 and one of the outer loops, we could just do the square root of 6 plus the square root of 6. And this would be equivalent to using x equals 2 here. So we should get the same thing here. And if we wanted to do another one, we could add another loop. And you can definitely see how using the recursive structure of things really helps simplify things, just because this would have been really hard to write using a while or for statement as well. Yeah. Yep, let's try it. Yeah, so does anyone have any questions on how to write this or like anything else we learned today? Oh yeah, I'll come look at it after class. Yeah. Okay, does anyone else have any questions? So here when we do x equals to 1, but just like in general, we kind of need to specify a base case. And since we're not adding anything else at the end, we'll just say it's square root of 6. Yeah, I guess we could have, yeah, because it is kind of an undefined picture as well. But yeah, so however you want to define it, you could change it up as well. Because I just use the same base case here, just to keep the square root of 6. But yeah, it was kind of a weird picture. But yeah, that's it for class today. And my office hours will be after class, like in the next room. Yep.
Oh, did Kate say something in the chat?